Modern data centers are designed around a simple idea. The equipment must keep running even when something fails. Servers process financial transactions, run cloud applications, store medical records, and power artificial intelligence systems. If power or cooling stops, those servers can shut down in seconds. Because of this, data centers are built with redundancy, which means having extra equipment available to take over when something fails. Redundancy is used in both electrical systems and cooling systems, and it is commonly described using terms like N, N+1, and 2N. Understanding these redundancy levels helps explain how data centers achieve extremely high uptime. What N means. The letter N represents the amount of equipment required to operate normally. In other words, N is the minimum number of systems needed to support the full load. For example, imagine a data center requires 3 chillers to remove all the heat produced by the servers. In this case, 3 chillers equals N. If all 3 chillers are running, the cooling demand is satisfied. But if one chiller fails, there is no backup capacity. Cooling performance would drop and the servers could begin overheating. The same concept applies to electrical systems. Imagine a data center requires 4 UPS modules to provide enough electrical capacity for the IT load. Those 4 UPS units represent N capacity. If one UPS fails, the remaining units may not be able to support the entire load. This configuration has no redundancy, and most modern data centers avoid operating this way. The most common redundancy level in data centers is called N+1. N+1 means the system includes one additional piece of equipment beyond what is required. That extra unit provides backup capacity if one component fails or needs maintenance. Let's look at a cooling example. If a data center needs 3 chillers to handle the cooling load, an N+1 design would install 4 chillers. 3 chillers run under normal conditions, while the 4th unit remains available as a backup. If one chiller fails, the backup chiller automatically starts, and the cooling capacity remains unchanged. Electrical systems use the same concept. Imagine a UPS system where 4 modules are required to support the IT load. In an N+1 design, the facility installs 5 UPS modules. 4 modules carry the electrical load, while the 5th module provides redundancy. If a UPS module fails or is taken offline for maintenance, the remaining units continue supporting the servers. N+1 redundancy provides a good balance between reliability and cost, which is why many enterprise data centers use this design. A more advanced redundancy level is called 2N. In a 2N system, the data center installs 2 completely independent systems, each capable of supporting the entire load by itself. Instead of having one backup component, the entire infrastructure is duplicated. For example, imagine a facility that needs 3 chillers to cool the servers. A 2N design would install 2 separate chiller plants, each with 3 chillers. One cooling plant supports the IT load, while the second plant provides full backup capacity. If the primary system fails, the secondary system can handle the entire cooling demand. Electrical systems often use 2N architecture as well. A 2N electrical system might include 2 independent utility feeds, 2 separate switchgear lineups, 2 UPS systems, 2 power distribution paths to the server racks. Each power path is capable of supplying 100% of the load. Servers are often connected to both electrical paths using dual power supplies, allowing them to continue operating even if one power path fails. This architecture dramatically increases reliability. Cooling systems in large data centers often combine multiple layers of redundancy. For example, a chilled water system may include N+1 chillers, N+1 cooling towers, N+1 condenser water pumps, N+1 chilled water pumps. Inside the data hall, cooling units such as in-row coolers or CRAH units may also follow an N+1 configuration. If one cooling unit fails, the remaining units increase airflow and maintain temperature control. This layered approach ensures that the failure of a single component does not cause the servers to overheat. Redundant electrical systems in practice. Electrical redundancy works the same way but with different equipment. A typical redundant electrical system may include dual utility feeds from the electrical grid, backup diesel generators, UPS battery systems, redundant power distribution units. If utility power is lost, the UPS systems provide immediate backup power while the generators start and take over the load. If one UPS module fails, the redundant module continues supporting the servers. This design ensures continuous power delivery to the IT equipment. Redundancy levels are closely related to data center tier classifications. Higher tier data centers include more redundancy and fault tolerance. For example, Tier 1 facilities typically have little or no redundancy. Tier 2 facilities often include N+1 components. Tier 3 facilities allow maintenance without downtime. Tier 4 facilities use fully fault-tolerant systems such as 2N architectures. These classifications help organizations choose the level of reliability they need. The purpose of redundancy is simple. Failures will happen. Pumps fail, power lines go down, equipment requires maintenance, and components eventually reach the end of their service life. Redundant systems ensure that when one component stops working, another system immediately takes over. This design philosophy allows data centers to achieve uptime levels of 99.999% or higher, which is often called 5 nines reliability. Redundancy is one of the most important concepts in data center engineering. Terms like N+1, and 2N describe how many backup systems are installed to keep operations running during equipment failures or maintenance events. Electrical systems and cooling systems both rely on these redundancy strategies to protect the servers that power our digital world. In the next video in this series, we'll take a closer look at data center cooling architectures, including chilled water systems, in-row cooling, and hot aisle-cold aisle containment. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.